Hey everyone, and welcome back to the Deep Dive. Today we're going to be looking at some fascinating research from Apple about making large language models more, well, efficient
For sure.
when training them.
Right.
And, as these models grow,
Right.
they demand more and more memory. And it's a massive
Yeah.
undertaking to train these huge models,
Yeah.
especially with billions of parameters.
No, yeah. And one of the biggest culprits for this,
Yeah.
memory bottleneck is something called the cross-entropy loss.
Okay.
The paper, Cut Your Losses in Large Vocabulary Language Models, says this loss calculation can actually consume like a crazy, like 90% of the total memory during training sometimes.
90%.
Yeah, 90%.
Wow. That's a lot.
It's a lot.
So what is it about cross-entropy loss that
Yeah.
makes it such a memory hog?
So traditionally, to calculate this loss, you have to create this giant matrix of scores. They're called logits.
Okay.
And you have to do this for every single word in the vocabulary. And, vocabularies can have hundreds of thousands of words sometimes. So as you can imagine, this matrix gets absolutely enormous.
Right.
And that's what leads to these huge memory demands.
Yeah, so the larger the vocabulary, the bigger the problem.
Yeah, exactly.
They give a really striking example of this in the paper with the Gemma 2DB model.
Right.
They found that just storing the log probabilities for a sequence of 80,000 tokens could use up all the memory of an 80 gigabit H100 GPU.
Wow.
Which is a lot. I mean, that's like your entire computer's hard drive just for one calculation.
Exactly. And, this memory limitation has real consequences.
Okay.
It limits the size of models we can train, the batch sizes, even the type of hardware we need.
Right. So it sounds like we need a better way, a more efficient way to calculate this loss.
Yeah.
And that's where Cut Cross-Entropy or CCE comes in, right?
Right. So CCE is this new method these Apple researchers came up with. And it basically eliminates this memory bottleneck from the cross-entropy loss.
Interesting.
And the main idea is to avoid making that massive matrix of logits entirely.
Okay, so how do they do that?
So instead of calculating logits for every single word in the vocabulary, CCE focuses just on calculating the logit for the correct word.
Okay.
And they use this reformulated mathematical approach to calculate the loss and its gradient directly.
Okay.
And this really cuts down the memory footprint without sacrificing the accuracy during training.
That's amazing. It's like finding a specific file on your computer without having to scan your entire hard drive.
Exactly.
So what are the sort of key innovations within CCE that make that possible?
So there are two main innovations that they describe in the paper. First is something called memory-efficient indexed matrix multiplication.
Okay.
This is in section 4.1.
Right.
Basically, it lets them strategically fetch and multiply only the pieces of data they absolutely need. So they're avoiding the need for that full matrix.
That makes sense.
Yeah.
So they're not dealing with the entire matrix.
Right.
They're picking out just the information they need.
Exactly.
So what's the second thing?
The second one's called memory-efficient linear log-sum-exp.
Right.
And this is in sections 4.2 and 4.3 of the paper.
Okay.
And it computes the loss and its gradient efficiently by basically taking advantage of the fact that a lot of the values in the softmax matrix, which is used to calculate probabilities, are super small and can be ignored.
Right.
So they're basically negligible.
All right. So it's kind of like realizing that you don't need to count every grain of sand on the beach to know how much sand is there. Right. You can just focus on a representative sample.
Exactly. And so by ignoring these really tiny, inconsequential values, it saves both time and memory without really changing the final calculations.
Cool. And then to make things even faster, they've implemented these using custom CD Triton kernels.
Yes.
I saw that in section 4 in figure 2.
Yeah, those custom kernels are basically like specialized instructions to optimize the calculations for their GPUs.
Right.
So it makes the whole thing even more efficient.
Awesome. So they're really combining these techniques.
Yeah.
So CCE drastically reduces the memory requirements of calculating the cross-entropy loss.
Right.
Do they show how much memory CCE actually saves?
Oh, absolutely. Yeah. The results in the paper, Table 1, are really impressive. For example, when they tested CCE with the Gemma 2 model and a batch size of 8,192 tokens, it only used 1.164 megabytes of memory for loss and gradient computations.
Wow.
But the standard method needed 28,000 megabytes.
Wow. So that's a difference of what, more than 24,000 megabytes?
Yeah.
So it's like taking a giant file and shrinking it down to the size of, I don't know, a small text document.
Exactly.
And they didn't have to sacrifice speed for this.
No, not at all. In fact, CCE is actually faster than some other methods out there, which is pretty remarkable.
Wow, so it's really a win-win.
Yeah.
This is a really impressive technique. I mean, it sounds like CCE could really change how we train large language models.
It really could. It definitely has the potential to let us train larger, more sophisticated models.
That's super interesting. We were talking about how CCE achieves these amazing memory savings.
Right.
And one of the techniques you mentioned was called gradient filtering.
Yeah.
Can you tell me more about how that works?
Yeah, so gradient filtering, basically, it uses the fact that in a softmax matrix, most of the elements are really small and don't actually contribute much to the gradient calculation.
Okay.
So CCE just skips computing the gradients for those elements.
Oh, that makes sense. It's like ignoring those old crumbs on the table when you're cleaning up.
Exactly.
It saves effort without affecting how clean it is.
Exactly. And by ignoring these minuscule values, they save time and resources without losing accuracy.
So the paper mentioned that they used a threshold to decide which gradients to ignore.
Yeah.
Can you explain that a bit more?
Yeah, so they use this threshold called epsilon, which is set to 212.
Okay.
And this value is specifically chosen because it's like the smallest value you can represent in the bfloat16 data type.
bfloat16, what's that?
Yeah, so bfloat16 stands for brain floating point.
Okay.
It's the 16-bit floating point format that's used a lot in machine learning because it allows for faster calculations, especially on these special AI chips.
Right.
And the paper mentions that using this threshold with bfloat16 makes things about 3.5 times faster without losing any precision.
So they're really fine-tuning it to get the absolute best performance.
Exactly.
It's like choosing just the right image resolution for a small thumbnail or something.
Exactly.
You don't need all that extra detail.
Right.
So another optimization they talked about was vocabulary sorting.
Yeah.
And that's also in section 4.3.
Uh-huh.
So how does that work?
So basically, they rearrange the vocabulary in a way that groups together tokens with similar probabilities.
Okay, so instead of having these high probability tokens all over the place, we're bringing them closer together.
Exactly. And by arranging the vocabulary this way, they can actually reduce the number of blocks they need to process during the gradient filtering, which makes things even more efficient.
Right. So it's like organizing a library by genre to make it easier to find what you're looking for and also to skip over the sections that you don't need.
Exactly.
It sounds like they've put a lot of thought into making CCE as efficient as possible.
They really have.
So they have a whole section in the paper where they analyze the performance of CCE.
Right, they do. Section 5 goes into that in detail.
Right, and Table 1 compares CCE to a few other implementations of the cross-entropy loss.
Right.
What were the results of that comparison?
The results were really impressive. They saw like an order of magnitude reduction in memory usage compared to the baseline implementation across all the models they tested.
That's amazing.
It is.
And they didn't have to give up speed to get that.
Not at all. In fact, CCE was often even faster than existing methods.
So it's really a win-win.
It is.
But they did mention one factor that seems to affect CCE's performance. It was the ratio of vocabulary size to hidden dimension in the model.
Yeah.
So what's that all about?
So it's interesting. As that ratio gets smaller, meaning the hidden dimension is bigger compared to the vocabulary size.
Oh, okay.
CCE's gradient filtering is a little bit less effective.
Oh, I see.
And that's because the number of tokens with significant gradients stays pretty much the same.
So the benefit might be a little smaller for models with really large hidden dimensions.
Yes, but the paper does point out that even in those cases, CCE still saves a lot of memory.
Okay.
It's just not quite as dramatic as when the vocabulary size is much bigger than the hidden dimension.
Right, so it's still a valuable technique even for those kinds of models. Did they test CCE with any other models besides Gemma 2?
Yeah, they did. They tested it with a few other models.
Okay.
In Appendix B, they looked at Gemma 2, 9B, Gemma 2, 27B, Llama 3, Phi 3.5 Mini, and Mistral Nemo.
And did it still work well with those?
Yeah, the results were pretty consistent across the board.
Nice.
They consistently saw that order of magnitude reduction in memory usage.
That's great.
Which shows that CCE is pretty robust.
Yeah.
And it can work across different model architectures and vocabulary sizes.
It sounds like CCE could become the standard way to train these large language models.
Yeah, it has a lot of potential.
It's exciting to see how people are finding ways to make these models more efficient.
For sure.
and more accessible.
Yeah.
This has been a really interesting conversation. We've been talking all about CCE and how it's really changing the game for large language models. So for our listeners who want to learn even more about this, where can they go?
The research paper, Cut Your Losses in Large Vocabulary Language Models.
Right.
It's a great place to start.
That's linked in our show notes, right?
Yes, it is.
Perfect.
You can also check out Apple's CCE GitHub repository.
Okay, great. Anything else?
Yeah, I think this research really highlights how important algorithmic efficiency is in AI.
Yeah, it's not always about throwing more power at the problem.
Exact.
Sometimes the best solutions are the most elegant.
Yeah, absolutely.
And I think that's a great point to end on. Thanks for joining us on the Deep Dive today.
My pleasure.
We'll catch you next time for another deep dive into the world of cutting-edge research.